Hello friends, this video is meant to accompany assignment 1.9 where you consider the stars and the elements in the universe, how the stars make them, and we explore the limitations of what even the stars are capable of creating. So let's dive right in and consider the stars we already know about. Once we know what they make, then let's explore from there. The early universe was that swirling mound of gases and an expanding cloud. Parts of it started clumping together through their gravitational forces, and then you see in this animation hotspots starting to grow. In those hotspots, it actually became like sun-like masses began to develop, and as gases coalesced and compressed to the middle, eventually the pressure and temperature was high enough that the light turned on, and that light became the first stars to glow in the very young universe. Over time, clouds of gas became enriched, and more elements were created by the stars and by the events that followed. We're going to explore that process of creating all the elements we know of today. Here we go. So take our sun. After it formed, eventually the materials around it settled down and started forming things like planets and comets and asteroids and dwarf planets, gas giants, all the things we know about here in our solar system. But have you ever considered where those elements to make all those things actually came from? They weren't created in the Big Bang. The Big Bang produced just hydrogen, a little bit of helium, and a smidgen, a trace of lithium, which is element number 3. So we have mainly a cloud of hydrogen. Well, you can't make solid ground out of hydrogen. It would just be a cloud, right? Okay. So we explore what's going on inside our sun, what we know is happening every second of every day and night for 10 billion years. Our sun is creating a new element. Down in the heart of that star, hydrogen is being converted at the rate of hundreds of thousands of tons every second. Hydrogen being converted into helium. That process where one little helium and another little helium get forced together and they become helium. So hydrogen, helium, fusion, yay, nuclear reaction. That's what's going on in the heart of our sun. Now, let's keep this idea going and consider what happens when our sun eventually runs out of all that hydrogen, right? And when that happens, the properties of the sun change. It changes color, it gets dimmer in color, and it looks reddish. The gravity is no longer holding it in that same size. It actually relaxes and grows really huge when it becomes this red giant. But it doesn't end. Okay, so take a look at this picture on your screen right here. You've got the sun on the left and the red giant on the right. What it is now, bright, dense, yellow, converting hydrogen into helium. The helium runs out and it grows gradually over time. It doesn't just change in one instant from sun to red giant. It is a slow growth over 1 billion years until it becomes red giant. But by then it's out of hydrogen completely. Well, what fuel does it have to keep going on? Well, the only fuel that it has is the fuel it's been making for 10 billion years. Helium, and lots of it. But it will go through that helium a lot faster than it burned through its hydrogen. And the red giant only lasts about 1 billion years. So the red giant takes that helium and it's combining it in its core, and it's pushing helium together to make things like carbon and oxygen and other elements, nitrogen, even phosphorus, right? So a red giant can make elements heavier than it made when our star was just the sun as it is now. Okay. So different size stars produce different types of materials. Let's keep this idea going here. This is a lot of information on one image. What I'd like you to do is consider the elements. Look at the top left. Look at hydrogen up there in the corner, okay? Hydrogen produced by our sun, which is a yellow star. Hydrogen is even produced by red dwarfs, those tiny little stars, just a few times bigger than, maybe a little bit bigger than Jupiter, okay? And then they're using hydrogen to produce helium. Look over here on the right. Now we've got bigger stars that are using helium to produce things like number 6, carbon, and number 7, nitrogen, number 8, oxygen. Okay, the heavier elements, but they're still really light. So stars are taking the simplest elements, combining them to make a little bit heavier. Then it takes those little bit heavier elements and makes even slightly more heavier elements. But there is a limit, my friends. I've put a stop sign on this periodic table. On the left side of the stop sign and above it, we've got stars creating all those elements. And then on the right, we've gone beyond what stars are even capable of creating. So take a look where the stop sign is. This seems to be a rule across the entire universe. No star, as it's doing its normal thing, no star can fuse in its core anything beyond iron. That's the Fe. That's the symbol for iron. Beyond that, we know these elements exist, so we figured out the only way for these elements to exist is for events to create them. They're created in a moment, not slowly cranking them out in fusion over billions of years, but they are created in a moment. Beyond iron, we're talking cobalt and nickel and copper, zinc and gallium, and you see all of them right there. Those slightly heavier than iron, they're produced when a massive star annihilates itself in a supernova explosion. That's where your heavier elements beyond iron come from. But we've got elements that are way heavier than iron. We've got gold and platinum. We've got the radioactive elements. We've got heavy stuff like mercury. We've got polonium. We've got radium. Think of the ones that are in nuclear fission, like uranium, sure, right? And plutonium. Okay, those are very, very heavy elements. They're radioactive, but they're really heavy elements. It is believed that they could only be created in a spectacular annihilation event, the collision of two super dense heavy objects that we call neutron stars. Now, two of these things collide. They actually annihilate each other and turn themselves. Every bit of their cores gets ripped open into the universe, and that force generates heavier and heavier elements. Very cool stuff. So I've left it on this slide for a long time. This picture here in the background is going to really help you to understand how you answer certain questions on your homework assignment 1.9. Okay. So as you need to, pause it here, do your answers to your questions, come back to this point if you need to. I'm going to keep going with our description here. So normal stars like our sun produce hydrogen and helium, but the bigger they are at the beginning, the more elements they can create. Check it out. Okay, so high mass stars never even start off like our sun. They are born huge. They are born super giants. Okay. And yes, right from the start, they're taking hydrogen, fusing it into helium. It's the easiest fuel for them to burn. But then, eventually, all stars run out of their hydrogen. Blue giants, blue supergiants, run out of their hydrogen very, very quickly. Our sun, you you can see it bright lower in the image here, lasts about 10 billion years. A blue supergiant might only live for 100 million years. So what is that? 0.1% of the amount of time that our sun is alive. So in general, the smaller the star, the longer they live. The bigger the star, the more massive the star, the shorter their lifespan, but the more things they produce. The supergiant, when it dies, it goes violent. And in that moment, creates those heavy elements, kicks them out in a cloud. Here in this image, a supershell. This is a planetary nebula, a supernova cloud of heavy elements that eventually become the birthplace of new stars, just like our sun was born from the annihilated remains of a previous supernova explosion. Very exciting stuff. This is an image of a supernova. Artist's impression, obviously. Now, these events are violent, scary violent, okay? It's been calculated that if one of these supernova events happens within about 10 light years of the Earth, the shock waves would not destroy our sun or our planets or anything, but it would be enough to rip the atmosphere and the oceans right off into space and leave Earth an empty, barren, ugly rock going around the sun. Okay, so it's enough to shred the more delicate parts of the planet apart. Luckily, none of these supernova events could happen within 40 or 50 light years, so we're safe. Nothing is close enough to be a threat to us. And yet, such a scary, destructive event as a supernova has its benefits to the universe as well. It creates those heavy elements that allow solid planets, rocky planets, and life to even exist in the first place. So there's your supernova, creating its heavy elements. Beyond that, we have things like neutron stars. What you see on your screen, this neutron star, artist's impression, obviously we've never taken a picture of one, but one step shy of a black hole, which is a star so dense it has crushed itself out of existence, but not quite that far, would be a neutron star. This is a collapsed core of a supernova, right? Remember, it annihilated itself out into space, but the center is still very dense, and it collapses down until it is just this tight little fast spinning ball of neutrons. This neutron star, right, is in fact full of energy and potential and possibilities to create those heaviest of the elements in the universe. If you take two of these and have them wander close to each other, they will start orbiting each other and eventually cycle down and combine together in the same spot. Boom. And when they meet, when they actually combine, they rip each other open completely and spill out into space a huge, violent explosion of heavy elements. And now we've got new clouds for more stars and planets to be created. So, let's go over some of the things that we've talked about today. Our sun, right, an aberrant star. We know that it came from a cloud in space. Okay, so some kind of a nebula, a cloud in space condensed, formed our star. Our star is producing helium made out of its ample supply of hydrogen fuel. Eventually that hydrogen runs out and it expands out to be a red giant. And that red giant begins using the only fuel available to it, all the helium that it's been making for 10 billion years before. So the red giant for about 1 billion years is cranking along, combining helium into heavier things like carbon and oxygen. Okay. After a while, the outer layers of our future red giant sun will start slowly drifting away into space as a cloud. It's a very gentle transition, almost like walking in a room and taking off your coat. It's not a violent You're not ripping off your coat, throwing it across the room. It's a very gentle outer layer. You take it off. That's what's going on with the red giant. And the white dwarf little spark is left in the middle. And the heavy stars, check these out, right? We have a really heavy nebula, okay? And it is compacting to form the really big stars. So a massive star makes a supergiant or a really big rare object called a hypergiant. And when they burn through their fuel very quickly, they annihilate themselves in a supernova, leaving behind the collapsed core of the supergiant or hypergiant neutron star. Some of them are heavy enough to make black holes, that is true. But the neutron star, don't forget, to make our heaviest elements, we need two of these neutron stars to come close to each other and combine and rip themselves open. And in that instant, the heaviest elements are created, the heaviest elements we know of. So, looking at the whole thing, here it is in one simple image. Clouds making stars, stars taking hydrogen and turning it into helium. The bigger the star, the heavier the star, they can make elements up to iron. Iron is the limit of what a star can create. After that, to make things heavier than iron, we need an event. A supernova event, the collision of two neutron stars, that's how we can get our most heaviest elements that we're aware of in the universe. So, sorry, jumping around here. That concludes our discussion of stars and elements. Go ahead and continue your work on assignment 1.9. Turn it in through Canvas as soon as you can and get your grade. Be ready to wrap up first quarter. And let me know if you have questions. I'm here for you. Look at the video in the description below, okay? Check out the video. It gives even more detail. It'll help you even more to nail the answers and get them absolutely correct on assignment 1.9, okay? Let Trace talk you through some of the things we've talked about, and he does an even better job of exploring these ideas. Check it out. And thanks for watching.